Hello, everyone. I'm happy to be here with you, and thank you for joining our session about democratizing MySQL, cloud managed to Kubernetes managed. My name is Flavius Mecea, and I'm going to talk about the story of building Presslabs operator for MySQL. This is a joint session with Platform 9, Sachin Manpathak. Unfortunately, he's not present today here, but he prepared a video for you. And his colleague Daniel is here to answer your questions. He will talk about a case study, how they migrate from cloud managed to Kubernetes managed SQL. First of all, I want to start by presenting the MySQL operator, and I will go through these 5 main topics. The context in which the operator was born, the needs that we had in mind, also what have changed and what we achieved. Also some challenges that we've encountered during development, and finally the project status and some future plans. First, let me introduce the company that I work for and the context in which the operator was born. We are a managed WordPress hosting company, doing business for more than 10 years. We started as a WordPress development agency, then we pivoted towards the hosting business. After serving both publisher and enterprise clients for several years, we came to realize that all companies in the global top-tier enterprise were doing the same thing, including us. So that's when we started thinking about open source infrastructure that could become the WordPress hosting standard, named Presslabs Stack. So it's not just about that stack, it's about our commitment to our mission to democratize WordPress hosting infrastructure and to share all accumulated knowledge. As part of our mission, we have 2 key objectives. We are currently building an open infrastructure using Kubernetes to run and operate WordPress, Presslabs Stack, and the other is building the MySQL operator for WordPress. You may know that half of WordPress hosting means hosting MySQL. So why we choose Kubernetes? First, it runs everywhere, from dev laptops, public clouds, private data centers. Also, it's open source. We had experience before with containers. Our core services already runs on Kubernetes, and it provides a lot of support for a lot of integrations like cert management, Nginx, Prometheus for monitoring, and so on. So, as part of the stack, we needed a way to automate certain operations, such as deploying, scaling, maintaining, and backups for MySQL. For that, we've identified several key requirements to focus on. First, we wanted something that is easy to operate, something that doesn't get in our way. Second, we need an elastic service to help us scale with the demand. And you all know that in hosting, service uptime is paramount. So we had to maximize the availability of our service. Also, no one wants to lose data, especially when it comes to someone else's data. And in order to reliably operate the service, our system, we need a method to observe what's happening from the top down to the request level. So with this in mind, we checked some of the available solutions and conclude that they were not suitable for us. For example, both Oracle and Percona operator perform group replication, which implies that they require more nodes to operate, at least 3, and this will increase the costs. So as great engineers do, we've ended up building a solution ourselves. A Kubernetes operator for managing MySQL cluster with asynchronous or semi-synchronous replication. So in the past 10 years, we've identified several must-have features which have been integrated into the operator to fulfill our basic needs that I just presented. So first is self-healing clusters. Without this feature, the operator doesn't make sense. And the operator has to continuously reconcile and solve replication issues. Also, highly available reads. This is true when more nodes are available. Also, virtual highly available writes. This provides us minimum of downtime due to fast failover. We will see how. Replication lag detection and mitigation. The operator takes lagged node out of rotation, or unhealthy nodes. And resource abuse control. This is very useful because it can limit noisy queries that can slow down your cluster. Also, automate backups and restore. This one speaks for itself. So all of these features have proven to be very helpful compared with our old setup. Now let's move on to the practical aspects of building the operator. In this figure is presented the entire system overview. The architecture is split into 3 main parts: the control plane, data plane, and monitoring. The control plane consists of the operator and its components, and are deployed using Helm, usually in a dedicated namespace. Here we have the controller itself and the orchestrator, a high availability and replication management tool. I will come back to it later in the talk. Now, the data plane represents the actual MySQL deployment, and is made of basic Kubernetes resources like pods, services, and so on, which can be spread across multiple namespaces. And last but not least, we have monitoring, which is performed by Prometheus, the standard Kubernetes monitoring system. Going deeper into the data plane, we can see that the MySQL cluster has multiple components. For example, the stateful set, that's the main component, and is responsible for provisioning pods and persistent volumes for each MySQL node. Also, there are 2 services: a master service that always points to the master node, and a healthy node service that points to all nodes that are considered healthy by the operator. The selection are made based on information gathered from the orchestrator. So your application will interact with those 2 services for writes and for reads, and is the application responsibility to split them by using app-specific logic or some dedicated software like Proxy SQL. OK, so internally, a node consists of several components, some init containers that are used for MySQL initialization and configuration. A main container, which is a Percona server for MySQL. We choose Percona because it's a battle-tested in enterprise environments, and it's a drop-in replacement for MySQL. And also, there are some sidecars. Some of them are based on Percona Toolkit, which are responsible for serving several actions like lag detection, monitoring, resource limit policy enforcement. And there is one more container that provides an endpoint for backups and for other nodes to initialize from. So now I want to mention some specific challenges that we had during the implementation of the operator, such as orchestrator integration. How we integrate orchestrator, a third-party tool, so we don't have to reinvent the wheel. Persistent volume cleanup. We have to manage persistent volumes ourselves, because the way Kubernetes does it is not suitable for MySQL. Operator upgrades and deploy. which is a common problem between the operators because Helm provides very modest CRD management and MySQL upgrades. This is a specific problem because usually it's done by humans and it's very hard to automate. So let me start by presenting the orchestrator integration. Orchestrator is a subcomponent of the entire operator. And it's the tool that handles MySQL failovers and topology. But it's not meant to be stateless, as operators usually are. So Kubernetes has a state, orchestrator has a state, and the operator doesn't know which one to listen to. Here I'm talking about an information flow conflict. To fix this, we choose to implement a reconciliation loop between orchestrator and Kubernetes, which at every few seconds reconciles the state between them. So on one hand, orchestrator is responsible for updating replication topology in emergency situation, in case of downtime, and to observe the current status of the cluster. On the other hand, the operator reconciles the desired topology into the orchestrator and provides service discovery for orchestrator. So even if the data from orchestrator is lost, the operator is able to restore that data. So as a conclusion, the operator takes decision based on information found in Kubernetes, which is always up to date because of the reconciliation loop. Another challenge was how Kubernetes managed persistent volumes. The MySQL data is stored in persistent volumes, managed by the stateful set. But this implies that when a cluster is scaled down, the volumes are not deleted. So after a while, when the cluster is scaled back up, the replication may fail. To fix this, we choose to implement cleaner, a worker that deletes persistent volumes when the cluster is scaled down, except for node 0, which is a special case, because that data should be kept as longer as the cluster exists to preserve data, to preserve losing data. Another challenge is a common problem in the world of operators, because how CRD management is still very painful. Currently, the de facto standard for packaging application is Helm. If you are a Helm user, you probably know that CRD management is still very painful, and Helm doesn't provide an upgrade path for CRDs. What is more, MySQL Operator is still in development, and CRD's specifications are subject to change. This made us to install CRDs without validation to minimize user intervention at upgrades. However, we hope that this is a temporary solution until Helms improve its support for CRDs. Now, a specific challenge is how MySQL upgrades are performed. Kubernetes already provides us some upgrade policies, like rolling upgrades for stateful set. But this is not exactly gentle for MySQL, because it can choose to update first the master, which will trigger a failover to the replica. Then, when the replica is updated, will trigger another failover, which is unnecessary and can be avoided if the master is the last one that is updated. So a contributor came up with an idea to use on-delete policy, which fits better our needs because the operator can choose which node to update. Therefore, we can control the order in which pods are upgraded. We try also other techniques like pod finalizer to block the pod deletion until the failover is done. But we hit a dead end because we misunderstood how Kubernetes finalizer works. It happens. Also, we tried using container lifecycle hooks, but it proved to be too complicated to implement. So we chose to implement on delete policy, which is still work in progress. Now I want to share with you the current status of the project and some future plans. So we plan to integrate with marketplaces like Google Cloud Marketplace, Operator Hub, and AWS Marketplace to make it easier for end user to install it. Also, we'd like to finish what we started, so we would like to introduce CRD validation and webhooks. And also, multiple backups policy for granular control over backups. And to make it easier for your application to connect to the cluster, we'd like to integrate proxy SQL. Instead of using that two services that I just presented, your application connects to the proxy, which will do the routing for you for writes and for reads. Now, the operator is still in alpha version, and we are really close to beta. We have a good feedback from community so far, and some major platforms already actively use it and contribute to it. So I would like to invite you to visit the project page on GitHub, and for any questions to join on the Slack channel, MySQL Operator Slack channel. Coming up next, I will play a video, a recorded video, with the second part of the presentation, where Sachin will talk about a case study, how they migrate from cloud managed SQL to Kubernetes managed. So let's hear Sachin.
Hello, everyone. My name is Sachin. I work as an engineer at Platform 9. Sorry I couldn't be there at KubeCon in person, but hopefully this video would give you enough insight into how we have been using this operator and what our plans are with this operator. And I'll be around to answer questions over phone as well. So just a quick intro to Platform 9. We are a company which offers open cloud services to our customers. And we have an offering which is based on OpenStack as well as Kubernetes. This is a managed offering of the cloud services. And we have around 300 cloud regions around management today. And we are managing quite substantial amount of compute. So it's like 500,000 cores of compute under our management. So how does this tie to the MySQL operator? We started back in 2014, and as a startup, we adopted the public cloud model. So using public cloud services, without investing too much into our IT infrastructure, we could grow our customer base fairly quickly. But at the current scale, the cost of public cloud is quite significant. Just our database bills amount to tens of thousands of dollars. And that's a significant drag for a small size company like us. So as I explained before, the 2014-2016 years were mainly based on public cloud services using exclusively RDS for all our deployment needs. We also used other services like the database, DNS, load balancer, etc., to fill up gaps. Then in 2017, we decided to move completely off of the public cloud in order to save on these costs as well as scale according to our requirements. So we started using our own offering, the OpenStack offering, to run the instances that we ran for our customers, and we ran this in our own private cloud environment. But at that time, we realized that moving off of database wasn't so easy because there was not quite equivalent service like RDS that you could simply run on a private cloud infrastructure. And that's when we found this MySQL operator created by Presslabs and tested it, validated it, and we are rolling it out in production. So the plan is that this year we'll be rolling out our production deployments, and by end of 2020 we'll have all our production deployments on this database. So what were the hurdles to running our own database as a service and getting out of consuming the public cloud-based databases? So first problem was that our deployment automation is set up with a self-service API-based model in mind. So the Ansible-based scripts that we have, they exercise the RDS APIs to create, scale, delete, resize databases. And we needed a very similar self-service API experience in our on-prem solution. We also relied on snapshotting and backups that RDS provides. And again, this process was also automated using the AWS APIs, and we needed a replacement for that. So because of these 2 points, we couldn't really adopt a solution where we create a database in a VM or on a bare metal server and then SSH into it to make changes. That would have broken our automation. Another problem was that by relying exclusively on a hosted MySQL service, we didn't really have database admins to save us from situations where a database backup goes wrong, or a database gets corrupted, or the service keeps crashing due to some bugs. We also required comparable performance with RDS because we wanted to sort of do a lift and shift, and we wanted to make sure that when we move a customer to an on-prem database, they shouldn't see any performance degradation. In addition, all our services were designed with expecting the MySQL as the backend. So when we switched databases, we wanted a drop-in replacement to avoid any unforeseen bugs and impact on our production environments. So with these goals in mind, we realized that using a simple VM-based approach might not be a good thing for us. And we started looking at self-healing platforms like Kubernetes to run our databases. That's when we found out about the MySQL operator and understood various features that it provides. And it basically ticked all our checkboxes. So this is how our comparison per our requirement looks like. We wanted a self-service, simple, open API, and that is provided by the CRDs that this operator exposes, and it hooks nicely into our automation. We wanted a drop-in replacement for MySQL, and since this implementation uses Percona, which is a proven MySQL database, we found it to be quite compatible. We haven't really discovered any breakages or bugs in our services due to switch in the database itself. We wanted fairly automated API-driven backup and recovery process, and that is provided by the database backup CR that MySQL operator provides. And we were able to switch our automation to use this API and take the backup to S3 as well as recover from S3 backups automatically. Since we are trying to do this at scale, so we'll have around 300 databases at least to manage when we go to production. We wanted a fairly automated and low-touch solution when it comes to handling failures. And we found that having a highly available database using Orchestrator is quite appropriate for our requirements. So we tested Orchestrator in the wild and found that it is able to recover from DB master failures in a quite automated and seamless manner. Given our experience with an existing cloud service, we wanted to avoid the vendor lock-in. And we wanted that ability and flexibility to switch the underlying cloud platform without disrupting our database as a service offering. And the underlying Kubernetes layer provides sufficient abstraction for us And we have enough confidence that we'll be able to run this database not only on our private infrastructure, but any other cloud that supports Kubernetes. And last but not least, we relied on the built-in monitoring that the database as service provided. We regularly check and generate alerts based on RDS events and certain thresholds. And the Prometheus metrics that MySQL Operator provides, we found them to be quite adequate for this purpose. In fact, they are more extensive than what a managed database service provides. So this database checked all the boxes that we needed, and we started implementing it on-prem. And this is how our infrastructure looked like. So as I explained before, we had an OpenStack cloud, which provided multiple availability zones. Each availability zone is essentially a failure domain for compute, storage, as well as networking. And although this diagram doesn't show it, our storage is also multiple AZ aware. And for example, the failures in AZ2 doesn't impact the storage in AZ1. So we have these three AZs provided by underlying OpenStack cloud. And for Kubernetes, we use the multi-master deployment where each master runs in its own availability zone. And we have a load balancer in front to round robin between the masters. To deploy databases, we also leverage this AZ concept. So the availability zone labels are bubbled up as worker node labels in Kubernetes. And the deployment of any database always has at least 3 instances. So 1 master and 2 replicas, and each one of them come up in a different availability zone. In addition, the orchestrator piece also runs with AZ, multi-AZ in mind. So there is 1 copy of orchestrator in each AZ. So a single AZ failure does not impact all the layers, including the Kubernetes orchestrator, as well as the database. In addition, we take backups of this database to S3 and recover from S3. So that's the layer of cloud infrastructure we're still using. So the current state is that we have validated and it works pretty well for our use case. And all our internal dev and test environments use this database today. To roll out the operator and to test the newer version of operators, we have set up 3 clusters. The dev cluster is used to validate changes in operator, ensure that there is no breaking change. After validation and testing, it gets promoted to staging, where in that area, we manage our internal dev and test environments. Once it gets proven there, it gets promoted to production to run actual production workloads. So our plan is to do 100% deployments of databases managed by MySQL Operator. And another nice thing out of this exercise is that we stumbled across the operator paradigm and the CRDs, which is very powerful for managing your infrastructure in a fairly automated manner. So we plan to use the same model for our Prometheus-based monitoring, log collection, API gateways, and so on. With that, I'm at the end of my presentation. Thank you, and I'll be around for questions. Bye.
No, thank you.
Hey, Sachin, can you hear us?
So if you have questions,
yeah, I can hear you.
Please ask.
So I'm Daniel. I work with Sachin, and unfortunately he couldn't be here today in person, but we went from on-premise Sachin to cloud-based Sachin, so sort of in reverse. Yeah, we'll relay questions that you have to him, and yeah.
Yeah, I would like to know what you think about the current production readiness of all of this. I mean, you said that it's alpha, beta thing. So at which point are you at the point where you think it's ready for production use?
We already use it in production, but not critical workloads. Right now we did a rewrite, something we changed, and it's a release candidate, and we have to improve some, as I said, orchestrator integration and to finish on delete policy implementation. And after that, it's almost ready from our point of view, of course. There is still need for a lot of tests. But we already use it in production, and such guys from Platform 9 already test and used the operator in, I think, in production, not sure, for some of them workloads.
Sachin, did you hear the question? It was, when are you ready to use? When do we consider this, alpha versus beta? What sort of, where are we along in the journey, and what's important for us when we go from alpha to beta and to GA eventually? Oh, think you're muted. Anyone ever muted on a Zoom call? Yeah. One person.
Can you hear me?
Yes, we can hear you. Is this your first time using Zoom?
Another questions for me?
Can you hear me? Or is it still?
Yeah, we hear you just fine now.
All right. Sorry about that. Yeah, so we have for almost a year now, and it's been pretty solid in replacing RDS. It's equivalent to RDS. It gives us a lot of performance data that RDS provides. We can monitor it pretty well. Most of the problems we hit were not actually because of the operator, but because the way our on-prem Kubernetes works. So we think it's production ready, and as I said in the talk, we have a lot of confidence that we'll be able to roll it out completely by end of this year.
Thank you very much for the talk. I have a double question. So first one is, how do you deal with growth when you have to change the persistent volume claim? How does that work with the operator? And the second one is, since you delete the persistent volume when you scale down, when you go up again, you have to replicate all the data, and what's the latency there? Or?
I'll start with the second questions. Depends. We use extra backup for backups, and we stream that backup to the other node. So if we delete that persistent volume, when it's recreated, and for small databases, takes few seconds, 1 minute. For large databases, takes more. And sorry, if you can repeat the first questions.
The first one was about the growth. So when the database grows, you have to grow the persistent volume claim. So how does that?
Yeah, you can resize the persistent volumes claim. Yeah. The operator doesn't do that. You have to do it manually. Okay, Kubernetes already provides you a method to resize it. Yeah. Okay.
I wonder if you could elaborate on why you will be interested in moving to proxy SQL instead of having two services.
To make easier to make it easier for people, for application to connect to it. It's easier to have a one endpoint instead of using some, I don't know, specific application logic. Usually applications use only one endpoint for reads and for writes, and not all of them have this split logic. That's why, but we will provide both of them, both solutions, because we prefer having in this way.
Yeah, I was going to ask, you use Orchestrator.
Yeah.
That's, I think, a service itself.
Yeah.
And I guess, as you were saying, that the source of truth for Orchestrator is the Kubernetes.
Yeah.
And you have some sort of sync. What happens when Orchestrator goes down and you have a failover situation? I mean, how long does Orchestrator take to recover itself?
Yeah. Orchestrator is highly available. It can be deployed in multiple clusters, so it can be highly available. It's used RAF to communicate and so on. If it's highly available, then it's always up, hopefully. If not, that's, for the moment, it's an undefined behavior. We still do tests to see what's happened. It may split the cluster into two separate servers, so it will be partitions.
I mean, so you can configure in the operator how many orchestrators do you have for availability, I mean?
Yeah, for now one, but usually three. We use three, and three orchestrator and three operators.
Okay.
So, another questions?
Sachin, do you want to talk about how we've been dealing with the growth of the database and how we resize persistent volumes? What's our experience been like? And then also discuss what our experience has been like with operator, the orchestrator, and what our plans are, when orchestrator goes down and there's an issue, for the MySQL operator to actually access the orchestrator.
Yeah, sure. So typically when we resize a database, we do have some interval of time where we can take the environment offline, resize the resources for the database and bring it back up. And it works pretty well with the operator in our case. For the orchestrator piece, as I mentioned, we have multiple availability zones, and each replica in the stateful set of orchestrator is spun up in its own availability zone. So we are really banking on the fact that failure of one availability zone does not impact either the database or the orchestrator workflow. We have had issues in the past where our networking went down, and as a result, one of the AZs was unavailable. And we were able to successfully have the orchestrator revert the master to a replica of the database. And this depends on the timeouts set in the orchestrator. And the setting we currently have is it waits for about 3 minutes before changing the master replicas. So we do have had a glitch in availability, but it is acceptable for the workloads we are running with this database.
Okay. Other questions? Then one more. Okay.
It's like. So this makes it easy to horizontally scale the cluster, but how do you deal with vertical scaling?
Yeah, we don't deal with that. Yeah, you have to change specification, and that will trigger a rolling upgrade, and will update. If you change the requirements, limits, and so on pods, you have access them on the MySQL cluster, CRD, and you can modify them, and that will trigger a deploy. Yeah, it's not online. Yeah, like upgrades. Other questions?
How long do you think it will take to arrive to stable release? Do you have any plans?
Yeah, we hope. Yeah, we hope in the next few months in the new release we have some, let's say, bugs that we have to handle. And after that, we want to integrate them in the operator hub and see the feedback from some users. And yeah, that's it. I think we already we hope to bring this to our clients at the end of this year. So it has to be ready because our clients depend on it. So thank you. Thank you for your time.